look at this question from the from this team selection test, the first question on it. So it was a geometry question, and the question basically said that we had a triangle. So let's draw that, and when we're drawing triangles, we want to avoid them being either isosceles or right angle because we don't want to assume anything about the triangle. So let's start by ABC, and then it's saying let D and E be the midpoints of AB and AC respectively. So let's this be E. And let's call this D. Okay. And then this is a bit some of you struggle to understand. So F is the foot of the altitude through A. So whenever you have an altitude, what that means is it directly drops down and it's perpendicular to the other side. So this is the altitude, this line, and this point here is the foot. So this is F. Okay. And now we had two important lines. We had the line DE, which got extended out to this side. And then also we had BCA and the angle bisector of it. And they intersected at a point out here, right? So they intersected at a point out here. So let's make that an alpha and make that an alpha. And let's label the angle bisector. This is already the midpoint as well. So we're going to make this a double length. And this is DB is also going to be a double length. And this is going to be single length AE and a single length EC. And what we want to show is that these 2 points and the circumcircle of ACF. So let's draw the circumcircle of ACF. So the circumcircle of ACF. So let's not let them intersect just yet because that's kind of what we're trying to prove. We're trying to show the circumcircle intersect at this exact point. So in other words, what this means is that let's call this point G. Okay, we're trying to say G, which is the intersection of ED and this angle bisector, goes through the circumcircle. So G lies on the circle, lies on circumcircle of AF and C. AF and C. What this means is that essentially this is true if and only if A, G, F, and C are a cyclic quadrilateral. And this is true. Well, there's multiple ways that we can prove this. So remember when you're trying to prove a cyclic quadrilateral, you want to take some segment. So let's take the segment AC and the two angles coming off that segment in the same direction. So AFC and AGC need to be the same. So AFC, oops, AFC needs to equal AGC. Okay, let me zoom out again. So we need to prove that those two angles are equal. Well, AFC is just 90. Now you could have done this in other ways. You could have said AGC equals ACG equals AFG. You could have said GCF equals GAF. You have lots of options. We're going to go for this one. In general, you want to find just some condition. Any of those conditions can work. So it doesn't really matter how you choose it, but you need to find something that looks nice. In this case, we already know that this angle is 90, and we're going to try and want to find some things about this AGC. So it seems like a nice one to go for. Now let's go back to our conditions that we have. So we have that DE is the line that connects up these midpoints. Now that's something that's happens very often in geometry problems. We have some triangle, then you have some midpoints here and some midpoints here, and you're somehow connecting up these two midpoints. Whenever that happens, you should immediately think parallel lines. And the reason is because this triangle is similar to this triangle, right, by SAS similarity, right, because it's half the length. And so therefore, this angle is equal to this angle, and this angle is equal to this angle, which are basically the rules of parallel lines. And so we have that this parallel line thing occurs. So what we now know is that DE is parallel to BC. You should always note that whenever you have two midpoints being connected in a triangle like that. So if we have these two parallel lines, well, we know that this angle BCD, so alpha is just the same as, sorry, not BCD, BCG, right? And therefore, that's actually just the same as CGE by our parallel line thing, by our parallel lines. So that angle is now equal to alpha. And so now we have this angle is alpha, and also this angle is equal to alpha. Aha, that means that we have an isosceles triangle. EGC is isosceles, So if EGC is isosceles, then we actually have that EG, the length, is equal to EC, right? And that length is actually just a single mark that we put down here. So that single mark goes over here. But if EG equals EC, then that's just the same as AE, right? As AE. But then now we have another isosceles triangle here. We have this triangle, AEC, AEG. AEG is also isosceles, Again, because of our two lengths being the same, AE and GE. So now that these two lengths are the same, we know that these two angles should also be the same. The two angles, EAG and E equals EGA. Let's try and figure out what those angles are. So we know that this triangle, EGC, that some of the angles is 180 degrees. That means that this angle here should just be 180 minus 2 alpha, right? And then that means that this angle here should just be 2 alpha because it lies on a line. Now, these two angles are the same, as we just said, EAG equals EGA, but they must add up to 180 minus 2 alpha, right? Because the angles in a triangle add up to 180. And if the two angles are the same but add up to 180 minus 2 alpha, then each of them must actually just be 90 minus alpha. So we can write this as 90 minus alpha here. Oh, but wow, this is 90 minus alpha and this is alpha. That means that this is just a 90-degree angle, a right angle. But that means that AGC is 90, which is exactly what we needed to show. Because once we have that, we know that AGC equals AFC, which means that this point lies on the circle as we want it, which is what we originally wanted to show. So that's all that's happening here. There's a few important steps happening here. There is a parallel line, and there are some angles, and an isosceles triangle, two isosceles triangles in the middle, and then just noticing that means that these 4 points create a circle. And that's all this question is. Let me know if you have any questions. Thanks.